Okay, so this is our discussion of going to extremes. So we have a number of questions to answer, and I'm going to actually do them out of order because some are much easier than others to think about. So the first one that we're going to talk about is there a largest integer? Okay, so you're imagining that some little kid comes running up to you and goes, I know what the largest integer in the world is. And so your answer to that child might be, okay, what is it? And whatever it is that they tell you, some obnoxiously large number, okay, what you could do to make that integer larger is simply add 1, right? And then you get an integer that was even larger than that. There are integers that are very, very large, like Google. Google is, let me think, it's 10 to the 100th power, I believe. There's a Googleplex, which is 10 to that power, all these different things. But again, you can still just add 1 to those things once you know them. And so is there really a largest integer? No. Whatever integer someone thinks is the largest, you can always add 1 to it. Now, you may get some kids who will go, but infinity. Okay, well, what is infinity? Infinity is actually not a number. Infinity is a concept, like forever is not a time, a specific time. So what you're looking for when you're looking for largest integers, you're trying to nail down a specific number, and infinity is not that. So infinity is kind of a place out beyond whatever we can think of. It's more of a concept. All right, so the same kind of idea comes up if we're talking about a real number. So if we think we know the largest real number in the world, okay, again, now you just won't have maybe whole numbers here. What you would be looking for, you could have something with a decimal point in it or something else. But again, you could just add 1, just like you did with the integer, and you would get a larger real number. So you really can never stop counting these things. Okay, these things go on forever and ever and ever, and you can always find the next biggest one very simply. All right, so our third thing that I would like to address is there a smallest positive number greater than 1? Well, for this one, let's kind of take a look at this visually on the number line. So here's your 1 and here's your 0. Sorry, the smallest positive number greater than 0, I meant to say. So what we're looking for is, what is the smallest positive number? What's right there? Okay, so what is a number that would fit right there? Can we figure out what the smallest possible number is that would fit right there? Well, that's difficult. We know it would probably be like a decimal, right? Like, let's just think of 0.1. 0.1 is pretty small, right? Can we think of anything smaller? Well, 0.05 would be smaller than that, right? And 0.01 would be smaller than that. And 0.001 would be smaller than that, right? And so we can keep on going. We can keep, making it smaller and smaller and smaller. And so if we're thinking about the smallest possible real number, as small as you make this, notice that I can make it smaller by bumping another 0 in here at any given time. So if I have somebody who tells me 0.0000000 da 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 da, and then eventually a 1, however many zeros they have, if I can squeeze 1 more in there, I can make that number smaller. So no matter how small a real number I can imagine, I can always make it smaller by bumping down a decimal place, can't I? So there really is no smallest positive number greater than 0, just like there is no largest integer or largest real number. Those go on forever this way, and I can keep squeezing things in here as long as I want to, and make them smaller and smaller and smaller, and never really get to a smallest number. All right, so then that brings us to our major question of the day, which is there a largest number that is less than 1? And that is related to the other question that's on the page. All right, so if we look again at our number line, what we're asking is there a number that fits right there? Okay, is there a number that is the largest number close to 1 without being equal to 1? And what would that look like? Okay, well, again, just like the 0.00 with the going on the other end of this part of the number line, we could start with maybe a guess of 0.9. But then I know that 0.99 is closer than that, and 0.999 is closer than that, 0.9999 is closer than that. So I can just keep adding 9s as long as I want and make a number that's closer and closer and closer to 1. So then, eventually you get to where, okay, let's just say I don't stop writing nines. Is that a number that is less than 1? Or is it equal to 1? And that brings us to our large discussion today. All right, so the larger discussion, I've got 4 different ideas that I want you to consider about whether this is equal to 1 or is it different from 1. Okay, so first would be space on the number line. So between these two things on the number line, is there, so if I zoom in a little bit, so there's 1 and here's 0.999 forever, okay? What is it that's between those two things on the number line? Notice that between 0.9 and 1, I could put 0.99. And between 0.99 and 1, I could put 0.999 and so forth. But if I put my 9s repeating, how can I figure out what would go between those two? If anybody has an answer, please put it in the comments here. All right, so there's number 1. Number 2, I'm gonna go with we can't think of anything. Okay, so there's no space between them on the number line, which means they must be the same spot on the number line. Okay, so another way of thinking about that is if they are different, so if 0.99 repeating and 1 are different, well, whenever we have two numbers that are different, we can find their difference. All right, and how do we find difference? Well, we subtract. So let's take 1 and subtract 0.999 repeating, okay? And that you can kind of make as many zeros as we need to cover up as many 9s as we need and so forth, all right? What is the answer to that? Well, let's kind of look at a pattern, all right? We've got some ideas over here that we can help with and see if we can figure out what's going on here. So if I want to find the difference between 1 and 0.9, I can do that pretty easily. That's 0.1. If I want to do the difference between 1 and 0.99, I'm going to have this. Keep going here. I need more zeros. I get that. So notice that every time I add a 9, my 1 bounces over a decimal place. So let's just say if I had, let's skip ahead a little bit. Let's say if I had 5 9s. Sorry about that messiness. So we did be there, right? Okay, so basically what happens is, make that a nicer 0. What happens is, after the final 9, I get to write my 1. So if it's only 1 9, I get to write it right away. If it's 2 9s, I delay it a little bit, 3 9s, and so forth. So I'm looking at, I get to write a 1 eventually when I have a difference between 1 and my number of 9s here. So what is the difference between these two? Well, I know that I'm going to put point and I'm going to put 0, 0, 0, and I'm going to do this. And when the final 9, after the final 9, I'm going to put a 1 here. Except there is no final 9. These 9s go on forever, so I never get to write my little number 1, which means this number here is actually 0, which means there is no difference between 1 and 0.999 repeating. Okay, so that's number 2 idea. So first of all, can we find something between them on the number line? I would challenge you that we probably can't, right? But that's not a proof per se. Number 2, if we were looking for the difference, well, there is no difference. The difference turns out to be 0. All right. Third idea, and this one is very relevant to our class because we just spent time changing repeating decimals into fractions. So recall that when we had 1/9, that was 0.111 repeating, and 2/9 was 0.222 repeating, okay, and so forth. We had a bunch of those. So when we got to things like 0.888, for instance, repeating, that was 8/9. Okay, so if I had 0.999 repeating, what would that be? Well, by our pattern here, that would be 9/9. 9/9 is 1. Ouch, there it is again. That's number 3. And here's 3 1/2, okay? Most of us are pretty sure, and we talked about this too when we did these, you could divide these out and verify that 1/9 is this, 2/9 is this, and 8/9 is this, and so forth, that you really do get those repeaters. But we're much more comfortable with certain repeaters, aren't we? Like 1/3, for instance, we've known forever, not forever, but for most of our lives, that that's equal to 0.33333, right? We even know that 2/3 is double that, isn't it? 0.66666, okay? So this is 2 times 1/3 is that, right? Well, 3 times 1/3 would be, all of these 3's would be 9's, wouldn't they? Oh, and 3 times 1/3 is 1. All right, or you could do it by addition. You could say 1/3 plus 1/3 plus 1/3, right? 0.33 repeating, 0.33 repeating, 0.33 repeating. All right, so there's 1/3 plus 1/3 plus 1/3. We know that that's one whole thing. What do we have over here? 9's and 9's and 9's. Oh my, oh my, oh my. All right, so repeating decimal wise, it also jives, doesn't it? All right, last one here. And this one, because a lot of people are suspicious of algebra anyway, most people don't like this one, but I will show it to you anyhow. So let's just say that our number that we're looking for is 0.999 repeating, and I want to figure out what is n equal to. Is there another way to express n? Okay, so the way we do this using algebra is we multiply both sides of this equation by 10. So then we have 10 times n equals 10 times this. Now 10 times a decimal will bump its place value over. So then we'll have 9.99, and then, all those 9's repeating here. So if you want to put the extra one there too, you could. To start with, just so you know that it's there for the next step. All right, so 10n equals 9.99999. Now, what we want to do is we want to subtract the same value from both sides. From this side, I want to subtract n. And now I know that n is equal to 0.99999. So from this side, I'm going to subtract the version of n that is 0.9999999. All right, so far I've multiplied both sides by 10. Now I'm going to subtract n from each side. So 10n minus 1n, it leaves us with 9n. Okay, 9.99999 minus 0.99999. Okay, that means the decimal part has been subtracted away, leaves us with 9. Well, so if 9n equals 9, we can divide both sides by 9. N equals 1. So that means that 0.99999, which was n in the first place, can also be called 1. So both of these are equal to n, which means they are equal to each other. All right. So I will leave you with that food for thought. So there are 3 and a half, 4 different ways that we've described how to explain that 0.999 repeating is 1. What I'd like you to comment in the comments of our forum is, which one is most believable, which one is least believable, and are you convinced in the end?